Hi, everyone. So today we are going to talk about centripetal motion and conservation of energy and how they play together. So first, let's review some centripetal principles with conservation of energy. Okay, so we've got a 2-kilogram ball is attached to a 10-pound test fishing line. That's 44.5 newtons. That means that it's going to break at that amount of force. The ball is released from rest at the horizontal position, and at what angle theta measured from the vertical does the line break? So let's draw this. We have a horizontal line with our mass, right? And we want to know at what angle theta here with the vertical, at what point does this break our test fishing line, right? So if we want to look at this, let's do a free body diagram. Okay, we've got our mass, we have our tension off at some angle, we have mg straight down, and remember this is not x and y, this is radial and tangential axes. So then we've got our theta right there. Notice that the theta is going to be the same from our free body diagram and our drawing that we have there. So that's going to be convenient. I have to convert back and forth from theta to theta. So we want to know what is the theta that this is going to break. Okay, so we need summation of forces with tension. So let's look at summation of forces along the radius. That would be tension minus mg cosine theta. Mg cosine theta. That equals mv squared over r. They didn't establish uppercase or lowercase. Okay, so we've got mv squared over r. Now this is our r. Okay, that is our radius. Now, if we want to find theta, we need velocity. It didn't give us velocity or radius, so that's an issue. But what we can do is we can do conservation of energy. So this is going to be a new strategy to put in your tool belt. If you do a summation of forces and you hit a dead end, sometimes you can use conservation of energy to actually find what you're looking for. So we have potential energy, potential gravitational energy, and we have kinetic energy. No friction, no springs, that's all we've got, right? It's just a bob dropping on a line in an arc. So it is dropped from rest, that is established. So that's rest. Our ZPL is going to be tricky here, right? Because the only position we know that even exists is this one right here. Okay. That has to be our ZPL because we have no idea how far that is actually going to drop before it breaks. So that has to be our ZPL initially. Okay, that's our ZPL. Now, this gives us an interesting scenario given our conservation of energy. Okay, so this is a new scenario we haven't done before. You start off with 0 energy, and that splits off into your UGF and KF. Now, I'm going to show you a little demonstration. This is one of those things where I'll do something mathematically that doesn't help us solve the problem, but just highlights a point. So if we look at this, if we subtract our UGF equals KF, okay, but if that's negative mg, but our ZPL was at the top, which means all our height is going to be measured negatively, right? Negative h equals KF. Okay, that means that those negatives can make a positive, which shows that your delta U will equal your delta K. As you increase your kinetic energy, you're also increasing your gravitational potential if you regard that as an increase, right? Because it starts at 0. And because these negatives cancel to become a positive. Okay, so that's just to highlight that this is a neat little trick here, that we have delta UG equals delta K, and we'll use that to solve our problem. So we can actually disregard the negative height. We can actually consider it positive because of this trick here. So we have, I'll start right here. Okay, we have mgh equals 1/2 mv squared. And we want v squared, right? So we don't have this v squared. We also don't have r. So it would be nice if we could solve for v squared in terms of the radius. So here is our v squared. We will just solve for v squared, not even v. We won't even square root it, right? We're just going to solve for v squared, but we would like it in terms of r. Now, the other thing we need to pay attention to is the height. What is the height that we are seeing here, right? So if this is 0, right? This is our ZPL at 0. Our height seems to be changing here along that blue line. Well, if we want things in terms of radius so that everything cancels, we can actually say that that would be r cosine theta, right? You can see that here if this continues down. R cosine theta would be the height, right? So let's turn this into mg times r cosine theta equals 1/2 mv squared. Now we just need to solve for velocity. We can get rid of the m's, multiply by 2, and I think you're done. 2gr cosine theta equals v squared. That's our v squared. And it is in terms of the radius. How convenient. So when we plug it up into our original equation, it'll actually cancel that. So that's going to be nice. So let's rewrite this. We have t minus mg cosine theta equals m times 2gr cosine theta divided by r. Now remember, this doesn't have to be squared. We solved for v squared. We're just substituting in for v squared. So the squared is actually disregarded because we've already taken it into account. So if we look here, that radius that we were not given, right? We have mass, 2 kilograms. We even have tension, 44.5. So we have everything else. We just needed to get rid of that radius, which we successfully did. So you get t minus mg cosine theta equals 2 mg cosine theta. Add 1 over, you get t equals 3 mg cosine theta. So we know that our tension is 44.5 newtons, right? That's our breaking point. Our mass is 2 kilograms, and we want theta. So using this guy, let's solve for theta. If we take tension divided by 3 mg, that equals cosine theta. So we will do a cosine inverse of t over 3 mg, and that will equal theta. So if we put this in, you've got cosine inverse of 44.5 divided by 3 times 2 times 9.81, and that will give you, what do I have? I've got 40.9 degrees. Now notice the work that we took, right? So that's going to break at 40.9 degrees below the, from the vertical. Now notice our method, right? This, all right here, okay, this is step 1. Okay? We did all of that first. Then we ran into that golden hiccup, right? V squared R we did not have. So came here. This was step 2. We used conservation of energy to get that v squared, and then we plugged it in here for a step 3, right? So this was a 3-step process. This is common when we have centripetal problems. We're going to do another one just like it next. But sometimes you have to solve for, start with summation of forces, go to COE, and then come back. So another problem for centripetal review. We've got a bead slides without friction around this loop-de-loop we've got in the picture. Okay, if the bead is released from rest at this height h, which is 3.5 times the radius, what is the normal force at point A if the mass is 5 grams? So let's actually do something very similar to last time, right? Well, let's start with a free body diagram and see where we get, because this doesn't, we're just finding the normal force. So this is actually a common centripetal problem. So we have what normal force is what we're solving for. We also have mg. Okay, this is at the top of the loop, so that's why normal force is down, right? So our summation of forces in the y are, okay, we've got normal plus mg equals mv squared over r. Again, we don't have r, we don't have v, we have mass, we need normal. Okay, so we need velocity again, right? This is, again, we are missing v squared, and we are going to get v squared in terms of r, hopefully, so that this will all cancel out and we'll have a nice, pretty answer. So let's look at our COE. Okay, we've got UGO plus KO. It said that it's frictionless, so you just have UGF plus KF. So we've started this height h. That's our initial. Our final is the top of the loop-de-loop. What should we set for our ZPL? Well, you actually have several options. Option 1 is right there at the initial point. Okay, this is option 1 for your ZPL. Option 2, you could set it at point A. That could be your ZPL. And then option 3 would be the ground. Okay, so we've got 3 options. In class, my students favored using point A because that was going to eliminate the final potential energy. You could also use 1 and eliminate the initial potential energy. When I solved this problem, I actually used the ground because all of my numbers were given to me, or I guess all the heights were given to me relative to the ground. So I had a height of 3.5 r. At A, the height would be 2 r. So I use the ground. It doesn't really matter which one you use. You'll get the exact same velocity either way. So let's do the ground. It's going to be the more complicated one because you're not canceling anything out. So I'll do the more complicated path first. Okay, so ZPL is the ground. Do we start at rest? Yes, from rest. So we can eliminate K naught. Okay, that is at rest. Hey, thanks. Thank you. So we will have potential energy to start with and potential energy to end with because our ZPL is at the ground level. So let's see, we have mg times h naught equals mg times h final plus 1/2 mv final squared. And remember, the whole point of this is to find v squared. So let's solve for v squared. We can get rid of the masses. Let's see, we have gh naught minus gh final all times 2. That's about it. Let's simplify that, right? We've got 2g times h naught minus h final equals v final squared. This would be 2 times 9.81 times, let's see, our initial height from the ground is what, 3.5 r, and then our height here would be 2r. So we have 3.5 minus 2, you would get 1.5 r. Oh, you know what, let's keep this like this. We'll do 2g times 1.5r equals vf squared. That will give us 3gr. So that is what we will put up top. And notice that it is in terms of the radius. How convenient, right? So if we want normal force, right, that is what we are solving for up here. Normal force. So we have normal force plus mg equals m times 3gr divided by r. R's will cancel. So you have n plus mg equals 3mg. Normal force, then just subtract that mg over, you get 2mg, which would be 2 times mass of 5 grams, so 0.005 times g, and you get, what is it, 0.0981. 0.0981 newtons. Bingo. So, similar way to solve the problem, right? We had to go through the summation of forces, right? We had step 1 right here with all of our drawings. Step 2 right here to get our velocity, right? And then step 3 was to plug that back in and get our answer. So similar process. Don't be too worried if this is something that you run into, because we've got these practice problems here that you can refer back on. Now we will look at one more slide, one more practice problem to see a couple different ways to solve these problems, not just step 1, 2, 3, summation of forces, COE, plug it back in. So let's talk about a roller coaster. Okay? We are moving with negligible friction along the roller coaster. Riders feel weightless at the top of a loop of r equals 20 meters. First, A, find the speed of the coaster at the top of the loop. B, find the speed of the coaster at the bottom of the loop. Then C, calculate h if the speed at the initial position, way up here, right there, if that speed is 10 meters per second. So if we want the speed at the top of the loop, right, that's something we've done before. Let's just get a free body diagram. Okay. Oh, wait, they did give us a hint here. Riders feel weightless at the top. If they feel weightless, that means that you just experience mg. There's no normal force there. If there is a normal force, that means that you can feel that you are being pressed up against the track. And that's not weightless, right? That's kind of the opposite of weightless. So here, our only force would be mg. So if we have mg equals mv squared over r, or m's cancel, we just want speed. So that would be gr square root equals v. And we have r, that's 20 meters. So this is the square root of 20g. And you get about 14 meters per second on the money. So that one, we just did summation of forces. You don't always have to go back and forth, right? Play your problem, work it out, start at one point, see where it takes you. Here we start at summation of forces, no problem, right? We didn't even need to go back to conservation of energy. Now we want the speed of the coaster at the bottom of the loop. So let's start where we have been. Bottom of the loop, you've got mg down, right? You've got normal force up. We still have centripetal motion, right? So that would be n minus mg equals mv squared over r. So if we want the speed, right, we would take normal minus mg, multiply that by r, divide by m, then you get v squared. That seems to have some issues, right? We don't have mass. mass didn't actually cancel, right? Because in this case, normal force, it doesn't equal mg, right? Normal force equals mv squared over r plus mg. So we can't just say, oh, well, normal force is mg, they cancel out. Can't even do that, right? So we hit a dead end. Now remember, start somewhere, see where it takes you, and if it doesn't take you anywhere, use a different approach. So for part B, for part A, summation of forces worked. We didn't even need COE. This time, let's see COE. Okay, summation of forces didn't work. So we want the speed at the bottom of the loop. It says frictionless. Whoops. It says frictionless, so we don't need to account for that in our COE. We're at the bottom of the loop, right? So we'll say the bottom is our ZPL. We actually know the velocity at the top, right? The top of the loop it has a velocity of 14 meters per second. It's just solve for the V final. That is our goal, V final. So we've got mass times g. What is the initial height? Well, if we're just looking at the top of the loop, the initial height would be 2r plus 1/2 m v naught squared. We know v naught is 14. Then that equals 1/2 m v final squared. We can get rid of all the masses. We have v final we want to solve for, so let's multiply everything by 2. So instead of 2gr, we have 4gr. Instead of 1/2 v squared, you just have v squared. Then let's take it all under square root, and that gives you v final. Right? We don't need to plug this back into anything, right? This is just our problem. So we've got 4, 9.81. The radius is 20 plus 14 squared. And you will come out to about 31.3 meters per second. So this just kind of shows us that it won't always be summation of forces to COE and then back, right? Sometimes it's just summation of forces. Sometimes it's just COE. You just need to start somewhere, see where it takes you, and if you hit a dead end, try the other one. If the other one doesn't work, check your first dead end. See if it really was a dead end. All right, last, C, calculate the height if the speed at the initial position is 10 meters per second. So this will be a COE, right? It's just talking about calculating the height. Okay, so if we want the height initially, we have initial potential and kinetic, final potential and kinetic. Whoops, I'm not adding everything together. They equal each other. So let's see, where would our ZPL be? Well, we know our final velocity is 31.3. That's actually at the bottom. So we could say that this is our ZPL and our final velocity is 31.3. Actually, you know, if you did this, you could find the height. So it wants the height, right? H is from the bottom of the loop to here, right? You could use the top of the loop and find that H, then just add to R. That's possible. But just to make things easier, let's make the ground the ZPL. Let's come to ourselves. So we have mgh, solving for h. We have 1/2 mv naught squared. We were just told the v naught is 10. We have 1/2 mv final squared. We just saw v final is 31.3. So we can get rid of the mass. Thank goodness, because we don't know the mass. And we need h. So h would be, let's see, we've got v final over 2, v final squared over 2, minus v naught squared over 2. Got to divide by g, but that looks like that's it. So let's take, was it v final is 31.3, square that, divided by 2, minus 10 squared divided by 2, all over 9.81. Put all that in, you should get 44 0.8 liters. Okay. So sometimes you don't have to do summation of forces, COE, and back. Sometimes you have to do just summation of forces and just COE. It just depends on your problem. But what we're trying to do here is build your toolbox, trying to figure out all the different ways we can solve these problems. Okay? And that is one of them. Summation of forces, COE, and then back again. All right, that's the end of our centripetal energy combination video. And we will continue on with chapter 8 in the next video.